just going to do some practice problems with combination circuits right now. And we're going to do some simple ones. This is a fairly simple circuit. We've got two in parallel, and let's give those some resistance. Let's say we call this one 500 ohms. Let's say this has 1,000 ohms. We're going to say R3 is 250 ohms. And we're going to say we have, what, 120 volts AC on this circuit. Although this is DC theory, we'll talk about a couple AC problems. Now, it's obvious that we're going to simplify this thing first, because if we just turn this into a simple single equivalent series resistor, then we've got a simple series circuit to look at. So if we look at this, and we see that we have R1 is 500 and R2 is 1,000, our equivalent resistor will have how much resistance? $333.33 ohms. Now we have another resistor, and we have 250 ohms here. So now we can come down and simplify this into one single series resistor, which is our whole idea. We want to simplify, simplify, simplify. So our total resistance would be 583.33. RT is 583.33, and our ET is 120 volts. So if we divide 120, looking at our Pioneer wheel, if we divide the voltage by the resistance, we'll get the current, right? So our total current should be what? 120 divided by almost 600. Thank you. 205 milliamps. Okay, 205 milliamps. Now, of this 120 volts, 205 milliamps, and 583.33 ohms of resistance, what number are we going to go back up into here? So what are we going to pull out of this thing and take back to the last simplification? Current, because it's a series branch. Okay, so we're going to pull this current right here out. I'm going to plug this into this thing right here. So our I12 is 205 milliamps. Let's say 0.205 amps for simplicity, 0.205 amps. And now we can see we have a voltage drop. So if we go up, if we write it P-E-I-R, and we did, okay, we have I and R, and if we're going up, we would get what? Our voltage drop, right? So we multiply 333.33 times 0.205, and we could simplify this into 205 times 10 to the minus third times, but say again? Thank you. So we have 68, sorry. 68.33 volts being dropped across this whole circuit right there, right? Branch of the circuit. Now, 250 times 0.205 is 51 what? 25. Well, it's got to be 0.66, but that's neither here nor there. Okay, so our voltage drop across this resistor right here is 51.25 volts. Okay, now we have one more simplification to go back to, And I want you to notice that this right here are our totals for that parallel branch, right? Now, out of that parallel branch, what number do we want to take up here? Voltage, because voltage is constant in parallel. So up here, we're going to put in E1, and it's a parallel circuit, so it's going to be the same voltage in both places, is 333.33. And down here, what's 1,000 volts? Oh, I'm sorry. Thank you. It's 68. That's right. The voltage is 68. That's the resistance. Let's get all this out of here anyway. Kind of a little bit of clutter there, but that's okay, I guess. Okay, so E1 is 68.33 volts. And here at E2, we have the same voltage at 68.33 volts. All right, so now we know that since we wrote it E, and then we would have I and then R, since we're going down, we know we would divide. So 68.33 divided by 1,000, we're just going to move the decimal place a couple places, right? So what current are we going to get? 0.683. Okay, and if we divide that by 500, 68.33 divided by 500, we will find what? Three what? Really? Okay. It doesn't seem right, but all right. Do what? 0.13? Oh. All right. 1366. Okay, now that's our current, right? Now, as a cross-check, we would add this current, 0.1366, and 0.0683. And what does that add up to? 0.205 amps? Okay, cool. So we know we're okay. We know our pure functional magic is working. Okay. All right. So that was a simple example, right? Okay. Now let's do another simple example. And let's just say that we have all right, so we have one more simple problem. And you can see that each of these things are in series, but they're both in parallel. So we're going to have to simplify. We're going to have to make a couple of simplifications, right? Okay, so our first simplification is going to look like this, where we just sum these two resistors, and we're going to have how many ohms of resistance on the right side? R34, 300 ohms. And then we're going to have another simplification. And we're going to have 250 ohms. Okay. And then our final simplification is just going to be one single series resistor, but it's a parallel pair that we're simplifying. So we're going to have to add 250 x to the minus 1 plus 300 x to the minus 1 is equal to x to the minus 1 is equal to 136.36 ohms. Now that's our total resistance, right? Oops. So here we're going to have, this is RT. So we're going to have ET, which is, we decided is 120 volts. So we're going to have a total current here of 120 divided by 136.36. And if you've got 136.36 in your calculator, don't hit anything else. Put in 120 divided by second function answer, and you get your answer much quicker. And it is what? 88 what? 8800. Okay, so 0.88, we're going to add one more zero just to remind us that in proper injury notation, that would be 880 milliamps. So now we're going to go back, and I think everybody can see that this is a parallel branch. So we're going to take our voltage up here. Okay. So 120 volts divided by 250 ohms is what current? Oh, it's 0.48? Okay. .480 milliamps, or 0.480 amps. Now, on our right side, we have 300 ohms. So let's look at our current over here. We have the voltage is the same over here, E34. It's still 120 volts. So we're going to divide that by 300. What is I34? What is it? 0.4. Now let's look at our total current, which is 0.880. If we add 0.4 and 0.48, what do we get? 8.8. I mean 0.88, right? Okay, so we have the right current. Okay, so now we have this set of totals for the left parallel branch. And what numbers are we going to put in there? This is a series branch that we're taking stuff into. So what are we going to take into that series branch? Current. Okay. Now, our current is constant through here, so it's 480 milliamps, right? So let's multiply 4.480 times 100, and we'll get our voltage drop across resistor 1. Okay, and we're going to multiply that times 150 now, 0.48 times 150, and that's going to be, say it again, 72 volts even. Now if we add those voltage drops up, not too surprising, we get 120 volts. Amazing, I tell you. Okay, so our pure functional magic's still working. Now we're going to take the right-hand totals, and we're going to take them over into this parallel branch, which is a series branch. Okay? That fascinated, huh? Thank you. All right, so. Oops. Okay, so we're going to take our current again, as somebody noted. We're going to plug that in here. And that's equal to 400 milliamps. So we're going to plug that in over here also. because current's constant. So we're going to multiply up again to get our voltage drops. And we're going to multiply 0.400 times 225. What are we going to get? 90 volts. And the other one is 30 volts. And we add that together, 120 volts. Amazing, I tell you. Okay? Is everybody with me right now? Everybody understand how to do these things? Nice, simple ones, right? Okay, cool. Let's do one more. Say again? If I don't see why not. Let's do a slightly more difficult one, and let's do let's see here. All right, let's say that we are looking at a slightly more difficult problem, and we look at it and we see very quickly that if we put a divider line right here, and look at everything to the right of that, that's just a series circuit, right? Series branch. So we can simplify that very quickly. Four five, not 3 5. Thousand ohms, right? Now let's look at how that relates to our next thing back. And we can see that this whole thing over here is in parallel with this resistor right here. Right? So now we have this thing, and we have decided that is 200 ohms. And from there, we're going to come down and make another simplification. So we're going to put our handy dandy TI-30X2S, and we're going to hit it clear a couple times. We're going to put in 200 x minus 1 plus 1000 x minus 1 is equal to, x minus 1 is equal to, and we get R3 through 4, 3 through 5, sorry. And that is, what is it? Okay. So now that, what is that? R3 through 5. That's everything to the right of the green line, right? So that's an equivalent resistor that resides right here, right? If we imagine that this part to the right of the green is gone and we have a single resistor here, that thing has 166 ohms of resistance, right? And what do we have coming to that? What do we have coming to that is two series resistors that are coming and going back. And so we're just going to look at that. And R1 is 50 ohms, and R2 is 150 ohms, and R3 through 5 is 166. So we're going to make our final simplification of the total resistance is 366.66 ohms. Okay. Now our total voltage is 240 volts DC. Okay, so I have a total current of what? 240 divided by 366.666666. What do we get? 0.654 what? One more number. 5, thank you. Amps, or 654.5 milliamps. Okay. Now, from this total information, what am I going to drag back into my previous simplification, which is this one right here, right? That's a series circuit, isn't it? A series branch, anyway. So I'm going to take this current. That's what I'm going to take down here. I'm going to plug in oops. So if I multiply up, I'll get my voltage drop across R1 and R2. And then if I multiply up over here at my R3 through 5, I'll get my voltage drop across everything to the right of the green line, right? Okay. So let's multiply up for R1. So 50 times 0.6545 is 32 point what? 7278 volts. And then E2 is 150 times 0.6545 is what? Okay, so now let's look at our last simplification over here, or part of our second to last simplification, where we got R3 through 5. What's our voltage drop across R3 through 5? 166.66 times 0.6545. Somebody? Anybody? 0.6545 times 166.66666. What is it? Okay, so our voltage drop across everything to the right is a series branch because we're creating an equivalent resistor here that is standing in for everything to the right of the green line. So this equivalent resistor is standing in for everything over here. And that's 3 through 5. And it's in series with this one and this one. So the current only has that path. if you only look at this equivalent resistor. Okay, so now, let me take that back out. And so we have 109.07 volts, and that's the amount of voltage being dropped across this equivalent series resistor that is represented by that green line. Okay? So now we're going to go back to the next simplification before that, where we had this resistor right here, R3, is in parallel with this resistor is in parallel with these two over here. You'd agree to that? Okay. Now, so our next simplification is this one right here where we had 3 and 4, 5. You see that? Now, since it's a parallel branch, what are we going to take from our 3 through 5 totals? It's a parallel branch. We're going to take our voltage up here, and we're going to have E4 through 5, 4, 5 is 109.07 volts, and R3, which is 200 ohms all by itself, is 109 also. Okay, so if we divide our 109.07 by our 200 ohms, what current would we get for this single resistor that's in parallel with everything to the right of it? I don't see my, where did my, oh, there it is. $545 milliamps. All right, now if we come back over here, we want to look at our other parallel branch, which is 3-4. And 3-4 has 1,000 ohm resistance. Everybody agrees with that? Okay. And we have 109 volts, so if we divide 109 by 1,000, what current are we going to get? Point zero. Oh, 0.1. Okay. It's not moving as much as far as I thought it was. Okay. Okay, so 109.7 milliamps is our current through 4, 5. Now this right here, our 1,000 ohms, 109 volts, and 0.1097. Those are our totals for just this right here. This path right here. So we're going to plug in our current because this is a series branch, right? Everybody see that? Okay. So since that's series, we're going to plug in our current. So oops. Oh, I can't pull it down. Darn it. Okay. What I can do is right over on the other side. So this is series branch. So it's going to divide what? The voltage, right? And it's going to divide up 109 volts, right? Okay, so we have a current of 0.1097, right? And on resistor 4, we have 400 ohms of resistance. So if we multiply up, what will we get? Our voltage, 0.1097. Okay. Let's come down and look at R5. Say again? What's that? Down here? Okay. So let's plug in our 600 ohms. I'm going to plug in 0.1097. We're going to multiply that up, and we're going to multiply up, and we're going to get, what was it? Okay. And 65.4 and 43.6, not too surprisingly, add up to 109. Amazing, I tell you. Okay. So still pretty simple. Okay. Actually, I think we're going to stop there. That's enough on that, I think.